is talking about X-ray observation on the NEP field. Okay, let's welcome.
Okay, hello everybody. So today I'm going to talk about the some X-ray observations of the Akari NEP field, and I just show some prospects for the net wide. And here's okay, on that side. Okay, so the some like around 2012, actually we wrote some Chandra proposal for the Akari NEP field, and fortunately we got some time. This is the basically the image, 3 color-coded image of the entire data set of the Chandra on the Akari NEP field. And this is more or less the exposure map of the Chandra, which covers the Subaru Spring-Cam field, which is designed to cover this Subaru Spring-Cam field. And the underlying image is the 15 micron data set for the Akari NEPD field. And we got the typical exposure of about between 40 and 80 kiloseconds. And the main purpose of the Chandra observation it was to identify highly absorbed, especially quantum thick AGNs. And I'll explain a little bit more. And before going to the our program, I'll just introduce you how the AGNs in the various absorption stages or absorption column densities look like in X-rays. This is from 0.5 to 500 kV range, and basically the ASCAS, XM Chandra, the classical imaging telescopes have their sensitivity up to like 10 kV, including E Rosetta. And then these are like say collimator experiment and Swift. And the Swift is a kind of coded mask experiment. NewStar is the first imaging telescope, which goes all the way up close to 100 kV or something like 80 kV. And actually the ART XC that we heard earlier remotely, will join this fleet. And let's say these are more or less typical of type 1, unabsorbed AGNs. And unabsorbed AGNs, but if you have more like a column density, then photoelectric absorption start to eat up soft X-rays. And these are basically more typical type 2 AGNs X-ray spectra. Still, we can see these things up to XMM or Chandra or E Rosetta here. Now, if column density goes beyond the 10 to 24 per square centimeter, then Compton scattering actually started to eat up even the like 30, 50 kV photons, and that basically all these are intrinsically the same velocity stuff, but just it starts to eat up even here. But still, like if you go down to this highest energies, you can really get some of the quantum thick AGNs, but still like there is a lot of loss of the sensitivity even at 30 kV at XC or NewStar regime. Let's see. Now it comes to Akari, and this is a kind of a very famous figure comparing the Spitzer's like photometric bands and the Akari photometric bands. And the advantage of the Akari observation, especially Akari NEP fields, is the availability of the say basically 3 filters that fills the this Spitzer's gap. And this happens to be the very, very sweet spot to pick up the AGNs at around the redshift of 1.5. And this is the very result produced by Takagi-san. And this is some figure that I put in our Chandra proposal. And this is the one of the AGN's photometry data set from like optical to all the way to infrared. And then this is a starburst model. And there is certain excess here at this around say around here. And these bands are really sweet spot to pick up this excess in the AGNs. And let's see. Let's see. Just give you the how the these AGN look like in the photometric band. Red is the observation by. Oh, sorry. The Spitzer band, and this is by Akari bands. And this is a redshift of 0.5, and this is for redshift of 1.7. And then, just because of this gap, it is somewhat hard to pick up the AGN only component with Spitzer, but with Akari you can really clearly see this. And I had Veronique just calculate how the fitting would result for certain AGNs as a function of redshift and with some AGN component. And this is a kind of error bar. Red things are the error bars observed with Spitzer, and the blue ones are observed by Akari. And actually, I tried to use it in my newer Chandra proposal, but unfortunately didn't get more time. But let's see. But for the moment, we actually made some tests. This is the some result of the DFIT. And which we derived the luminosity of the infrared AGN component on this x-axis. And on y-axis, this is the X-ray luminosity. Okay? And these triangles are for known type 1 AGNs. And more or less they are lined up on this line. But if you have the there are a whole bunch of stuff down there. So we drew a line. If it had the Coulomb density of 10 to the 24 per square centimeter, it's slightly redshift dependent. These guys should come below this line. So we picked up the things that are below this line. And at that moment, we found some 28 of these things and what we call strong Compton-thick candidates. And now, for these Compton-thick candidates, one of the very property of the Compton-thick agents are like a very strong equivalent of this I and K alpha line at 6.4 kV. And just look at this. And of course, there are iron on those things, but of course, continuum is big, so equivalent width is not that big. So just going. So what we did is the made a stacking, and also the it is basically the stacked spectrum of these 28 AGNs in the rest frame in energy. And what we got is this guy. It's just about 1.6 sigma. And equivalent width is still consistent with Compton-thick AGNs. So the what we are kind of sure is that among these 28 objects, there are some number of Compton-thick AGNs. Let's see. And So the next step is like we are really working hard to get spectra of these X-ray sources as well as composite agent candidates. And this is a summary of our entire group's spectroscopic program. And some years ago, Marius Carozos made a really nice summary of spectroscopy, and I basically took it over and then included the results of the many spectroscopic programs afterwards. Especially, my group ourselves use the ground telescopius Canarias big scan time to observe mainly the X-ray AGNs and infrared selective AGNs. And also the Mac and Helen Kim actually contribute the taking spectra of these AGNs and alongside. And we now have the later this month, our colleague at Potsdam's Mirko Krumpe actually will take the large binocular telescope, some spectra of the other with large binocular telescopes. Let's see. And why it's really important is that this is the spectrum of one of our composite agent candidate. And what we get is this guy. Right here, it's a broad line. If it's magnesium 2, then spectroscopic redshift is 0.73, and the Keck diamonds by the Mac and Helen Kim get spectroscopic redshift of 0.708, and I think if there is some bar type feature here, then they will be consistent. But in any case, the composite candidate classification was based on the photometric redshift, assuming the photometric redshift was 1.575. So if you have the different spectroscopic redshift, you have to redo the SCD fitting. So it's important, and that's why we really try to keep the spectroscopic programs. And okay, and I think I'll skip that. I'll just explain. This is kind of the object that we found in our X-ray observation, X-ray source, spectroscopy of an X-ray source. And this is a spiral galaxy, and there are lots of H2 nodes here. And we put this is the position of the X-ray source. And then we put slit here, and we put this one and this one. And
almost 3 minutes.
okay. Okay. These two globes, and then so X-ray luminosity is something like a 2 × 10⁻40 ergs per second, which is the kind of typical of what we call ultraluminous X-ray source. And we put, and this is the some diagnostic diagrams of this ULX globe, or this happens to be X-ray source, and this is a pure star-forming globe, and then we kind of find kind of really marginal evidence that the ionization of this nebulous is probably contributed by an accretion source. Okay, so now it's X-ray prospects for NAP wide, and then let's see. I'll just give you some information. Of course, you heard about E Rosetta and XC, especially E Rosetta. We can do the same experiment to find the highly obscure AGN. We found some 28 somewhere around here, and we are trying to increase the sample around here. And so here are some prospects, and especially we expect to find the 270 semi-compton-thick Asian candidates under a certain model, and this is a kind of expectation because they are not only the X-ray sources themselves, but it's rather the infrared detected Asians with upper limits in X-rays. Okay, and also they I think this is more or less what I wanted to say. So we summarized, we obtained Chandra data over central region of the Akari NAPD field with the primary purpose of identifying compton-thick Asians. And I just keep the explanation here. And in our preliminary analysis, we had 28 strong compton-thick Asian candidates, and especially this is a kind of an older version. So I'm really eager to try out the result of a newer SED fitting result to check the stability, and then we are doing optical spectroscopy. And also, we have a lot of expectation on the Akari net wide plus HSC and Rosetta combinations. Okay.
Are they new sources? Like, say, you have. So these 28 sources are your candidates, are
yes, right.
mainly identified compton-thick
Really identified, more like not individually. Not individually, I mean many. Okay.
What I mean is that are they already identified as compton-thick sources in some other catalogs like Swift or Newstar?
No, not only. Of course, there are many depths and widths, and there are lots of surveys. But especially what is strong for us is the regime around redshift 1.5, where we can actually use very good Asian component measurements from the infrared. So that's.
Okay, just a quick question.
I have a question.
Yes, please.
So I'm just wondering, when you do the stacking for the compton-thick candidates,
Yes.
I wonder what the typical star formation rate of their host galaxies are, and if those star formation rates are high enough that some of the ionized signals might come from, say, 6.7 keV emission.
Well, I don't have the star formation rate on hand, but I believe that we don't really see 6.7 keV emission in distant galaxies. Yeah, I think they're well, I don't think the possibility is not large. That is contributed much by this 6.7 kV from star formation region.
Okay, yeah, thanks.
Okay, so it's time to move on. Let's start the speaker again. Next speaker is Professor Dennis, coming from France. He's talking about multi-wavelength study of galaxies.